Let's begin with the problem statement for this project. So the problem arises when the midterm elections approaching in 2018 and people are looking for more information about the voting process. And in this section, we will focus on integrating the machine learning concepts to better understand the electoral process. This project will mainly focus on the population segmentation using the public data set from the US Census on demographics by different US counties. The outcome of this analysis are natural groupings of the similar counties in a transformed feature space. The cluster that a county belongs to can be leveraged to plan an election campaign, for example, to understand how to reach a group of similar counties by highlighting messages that resonate with that group. So throughout the project, we will have an overview of the data science workflow using the Sagemaker to perform the unsupervised learning using the principal component analysis. So I will start with importing the necessary libraries that are required to run the project in our notebook successfully. So we import the pandas, NumPy, OS, and the IO libraries first. Then we import the matplotlib followed by the Boro3 and the Sagemaker libraries. We have already discussed all of these in our former sections. And next we have the pandas option to set the max rows and columns options. This is for the display so that we can see all the columns of our dataset. Otherwise, we only see a few in our dataset. In the next cell, we import the get execution role module, and then I will store the Sagemaker session and the execution role in the variables Sagemaker_session and the role. Now let me print and show you the role. So it is the same as we created at the time of notebook creation. So before we start importing the dataset from our S3 bucket, let me tell you that the dataset for this project can be downloaded from the Kaggle resource, and the link is provided here. When you download the dataset, you will notice that there are multiple files in there. I have only used the ACS 2015 county data file and uploaded in my S3 bucket. For that, I have created a bucket with the name population segmentation. And in the next cell, you can see that we have created a variable to access the bucket with the name population segmentation. Also, storing the S3 client information in the variable S3 client. The dataset file we are using contains multiple files in there. So this cell, when I execute it, it will provide us the list of all files available in the county data file we uploaded in the S3. And here you can see that we have the files as ACS 2015 county data.csv and then other files as well. So we only need the CSV file as of now to start with our data exploration. So for that, in the next cell, here we have accessed the index 0 file, which is our first file of the CSV format. Let's run it. So now the data_key variable contains the name of the CSV file. Now that we have the data key, let's give the full S3 path to read the CSV file as a data frame so that we can have the county's detail. That's what I have done in the next cell. And here in line number 1, we provided with the complete S3 path with the arguments, and then in the variable named counties, we are reading the data frame out of the CSV file in the S3 path. Let's look at the data frame we have loaded. So I'm interested in looking at the head of the counties variable. Let's run this line. And here you can see that we get the first 5 rows. So we have the census ID, state, the country, total population, and out of those we have the total of men and women, the Hispanic population, and all the detailed information are available here. So we have a large amount of information to extract much useful information, and here you can see that we have so many features or the columns in this dataset. If you go back to the first cell on the top, here we have written the last 3 lines to display the maximum rows and columns. If you don't write these lines, you won't be able to see all the columns in the counties variable. Alright, so we have successfully loaded the dataset. So in our next lab session, we will start with performing the exploratory data analysis on this data frame for the counties. In this lesson, we will perform the exploratory data analysis on the dataset for the counties we loaded previously. Let's begin with looking at the shape of the data so that we have an idea of how many data points we will be working on. So we have 3,228 rows and 37 columns. Now let's look at the information of the dataset so that we have an idea of missing information, and then I will drop them out to make our analysis easier. Alright, here is the detail of all the columns. So we have some incomplete data points in the income column, income error, and the child poverty column. So we will drop all the rows having incomplete information. Let's run this cell. And here you can see that after dropping the incomplete rows, we are left with 3,218 rows and the columns are the same. Next, I'm using the .describe function to look at the statistical analysis on our dataset. And here we get all the statistical data for our features in the dataset. Let's start with the visual exploratory data analysis to make our analysis a bit interesting. So over here, I'm interested in looking at the histograms for the features that include professional, service, and office. Let's run it. So we get the histograms for the three selected features. We can observe the distribution of the counties that have the percentage of workers in professional, service, and the office occupation. The distribution of professional workers reveals that the type county has around 25 to 30% professional workers with a right skew and a long tail, and a professional worker percentage topping out almost 80% in some counties. And for the other two occupations, the number are greater. Now moving on to the feature engineering part. First, we have the data scaling part. Let's combine some of the descriptive and referenced columns such as state and country and leave the numerical features column. We can now set the state and country as an index, and the rest of the numerical features become the attributes of each unique county. And here you can see that the state and the county names are now merged together and are placed in the first column. The rest all the columns contain only the numeric values that will keep us make our analysis easier. If I quickly show you the list of features that contain the numeric values as of now. So this is what we are finding here in the next cell. And here we have a total of 34 features now, and these are all their names. Now we need to standardize the scaling of the numeric columns in order to use any distance-based analytical method so that we can compare the relative distance between different feature columns. So we can use min-max scaler to transform the numerical columns so that they also fall between 0 and 1. I'm using scikit-learn library and importing the min-max scaler. The scaler method I'm using is here in the second line of the cell, which is the min-max scaler. So for the scaled values of the features, I have used a new variable named as counties_scaled. This contains the scaled values in the range of 0 to 1. Let's run it. Alright, so here we have the same table, but this time all the values lie in the range of 0 to 1. So we get the scaled output here. Now let's have a look at the statistical figures for this scaled dataset. So for that, we will use the .describe function. So here we have the statistics for the scaled dataset. Now with this scaled dataset, it becomes easier to analyze the dataset with the help of the PCA algorithm, which we will be looking at in our upcoming lab sessions. In this lesson, we will look at the data modeling part for this project. So starting with the dimensionality reduction, we will be using principal component analysis to reduce the dimensionality of our data. When there are a lot of variables, or you can say features that are more than 10, then we are advised to do PCA. PCA is a statistical technique which reduces the dimensions of the data and helps us understand and plot the data with lesser dimensions compared to the original data. As the name says, PCA helps us compute the principal components in data. So principal components are basically vectors that are linearly uncorrelated and have a variance within the data. So here we first import and call an instance of the PCA Sagemaker mode, where we are importing the PCA module, giving the bucket name and the number of components, which is the total number of features in the feature list minus 1. Then we specify different parameters of the model. These are the resource configuration parameters, such as how many instances to use during training or what type of instance to use. Or they can be model computation hyperparameters, such as how many components to use when performing PCA. Be sure to specify the bucket name for a bucket in your account where you want Sagemaker model parameters to be stored, which in my case is the same bucket name, and a folder with the name counties, as you can see in line number 8. Next, we prepare data for Amazon Sagemaker by extracting the NumPy array from the data frame and explicitly casting to float 32. In the next statement, we create the model calling the fit function. The record set function in Amazon Sagemaker PCA model converts a NumPy array into a record set format, that is required format for the input data to be trained. This is a requirement for all Amazon Sagemaker built-in models. Now we call the fit function on our PCA model, passing in our training data, and this spins up a training instance or cluster to perform the training job. Let's execute this line. And it will take a while to generate the model. So I will pause here and we will continue with the PCA model attributes accessing in our next lab session. In this session, we will learn how to access the model attributes for the principal component analysis based model we just created. So if you go to the Sagemaker dashboard and over here under the training tab, click on the training jobs, and here is the model we just created. Here is the model we just created. So you can see the name for this. We have PCA-2021- the current date and time, and it shows completed, which means our model is successfully created. So select this name and copy it. Moving back onto our Jupyter notebook, over here in the first line of the cell, paste the name of your job here. Next, we are going to access the model.tar.gz file, and this is the file in which our trained model metadata is contained. So let's access the underlying model parameters, and before I access it, let me show you this model file in the S3 bucket. So we will go to the defined location as in line number 2. First, we go to the S3 bucket, and then in there, if you remember, we made this population segmentation bucket, and in there we have our counties folder, and inside this we have the output folder where our model file is saved, this one. So here the lines 4, 5 and 6 will download the model file in the current notebook instance work directory and unzip the model.tar.gz file. Now let's run this cell. Alright, so the cell is executed with success. After the model is unzipped and decompressed, we can load the ND-array using MXNet. So ND-array is an API of an MXNet. The ND-array API is defined in the ND-array package, and it provides imperative tensor operations on CPU or GPU. It also represents a multi-dimensional and fixed size homogeneous array. So here I'm importing the mxnet library and loading the nd array. And this load functions of nd array loads an array from this file. Now let's talk about the PCA model. It contains three groups of model parameters. First one is the mean. This is optional and is only available if the subtract mean hyperparameter is true when calling the training step from the original PCA Sagemaker function. Then we have the v part, which contains the principal components. And the last one is the s part, that are the singular values of the components for the PCA transformation. This does not exactly give the percent variance from the original feature space, but can give the percent variance from the projected feature space. Now let's extract the s and v parameters from our model. So in this cell, I'm extracting the s parameter in variable s and that for the principal components in variable v. For s, we can get an approximation of the data variance that is covered in the first n principal components. The approximate explained variance is given by the formula, the sum of the squared s values for all top n components over the sum over squared s values for all the components. And from v, we can learn more about the combinations of original features that make up each principal component. So in this line of code, we now calculate the variance explained by the largest n components that we want to keep. Let's take the top 5 components. Let's run this line. We can see that the largest 5 components explain approximately 72 of the total variance in our dataset. In this cell, I have created a function that will calculate the variance with the help of n numbers of components. So here in the definition for the explained variance functions, we are using the same formula. And the for loop runs for n equals 1 to 10. Now let's run this cell. And here we can see the variance with top 1 to 10 components. We will stick with the top 5 components. Now in this cell, we have the variable s underscore 5, which select the top 5 s variable values. Then we have the v underscore 5, which selects the top 5 v variable values. And as these columns have their labels from 28 to 32, so let's change them to 0 to 4. Now as we are done selecting the top 5 components, we will now examine the makeup of each PCA component based on the weightings of the original features that are included in the components. So now let's run it for the first component. So the graph is generated for PCA component makeup 1, and we can see that the component describes an attribute of a county that has high poverty and unemployment, low income and income per capita, and high black population, that is Hispanic population, and the low white population. So you can also name this component makeup as poverty or unemployment, as it is very much relates to it. Now let's run it again for the second component. For the second graph, which shows PCA component makeup 2, we can see that this component describes an attribute of county that has high self-employment and public worker populations. Similarly, you can perform the same for the third, fourth, and fifth component as well. I have listed here my observations for each component analysis. You can also change it according to your insight into the component analysis. Alright, so this is it for this lab session. In our next lab session, we will look at how to deploy the PCA model and then predict the results in accordance with the individual components for each county. In this lesson, we will look at deploying the PCA model we have created and then extract the useful information out of it. So I have used here the initial instance count of 1 with the instant type as MLT2 medium. I have already run this line beforehand to save time, as it takes much time to deploy, where at the backend it creates the endpoints for us so that the model can be used. Here I have stated the component list. The component 1 is represented by the poverty and unemployed population. The second component represents the self-employed and public worker majority. The third one represents the high income, professional and the office workers, whereas the fourth component represents Black or Native majority population, as well as the public professional workers. And finally, the fifth component, which represents the construction and commuters in majority. In the next cell, I'm declaring the PCA list. You can either give them the name of the components itself, and here I have used the component number label itself. Next, let's run the predictor and pass our original data set to the model so that we can transform the data using the model we created and save the result in the result_PCA variable. So it is now executed. Then we can take the largest 5 components, and this will reduce the dimensionality of our data from 34 to 5. Now let's run this line. Now we have created a dataset where each county is described by the 5 principal components that we analyzed earlier. Each of these 5 components is a linear combination of the original feature space. We can interpret each of these 5 components by analyzing the makeup of the component shown previously. Let's run this cell and look at the first 5 predicted values for the counties transformed. Now that we have the result in front of us, for all the state and county names, we have their weights for respective components. Let's take the first one. We have the Alabama State and Autauga County. For this, we can see a positive weighted value for component 2, which is majority of self-employed and public workers. Also, we can see the same for component 2 having the positive value for Alabama Barber County in the 3rd row and Bibb County in the 4th row. If we compare 3 of them, we can see that the Alabama Barber has higher value than the other 2 counties, which means the self-employment and public workers are more in numbers in this county. In the same way, if we talk about the poor and unemployed population, it is high in Alabama Bibb and less in Alabama Baldwin County. So you can see how this enables a prediction ground on the dataset that we had with us, so that anyone can analyze the dataset as per their particular requirement. Maybe someone is interested in working for the poverty and unemployed population, so they can focus on that county during the elections. Or it can be any other case as well. So this is how the principal component analysis can be carried out. Just a quick recap to this, where we started from the county data asset, then we performed the exploratory data analysis, followed by the model training for PCA. And then we looked into the model artifact having insight to the components, where we focused at the top 5 components. And then we used this to get our results on the test dataset, extracting some useful information. Now for every project, the last step is always to delete your endpoint. Just run this line, and this saves you from additional charges being incurred. The next project in our upcoming section will be the continuation of the same project, where we will use the k-means to segment the population of counties by the 5 PCA attributes we have created. See you then.